All right, settle down, everyone. Today we're going to talk about time, and I'm going to tell you right now, this is going to blow your mind. Not because I'm so smart, but because nature is so damn weird. Oh, what is time? Go ahead, somebody tell me. What is time? It's what clocks measure. Okay, good. That's what I would say too. But now, let me ask you something trickier. What's a clock? It's a thing that measures time? See what happened there? You just went in a circle. You told me time is what clocks measure, and clocks are things that measure time. That's like me asking you what's an elephant, and you say it's the thing that looks like an elephant. You didn't tell me anything. Let me tell you a story. When I was a kid, maybe 7 or 8 years old, my father and I would take walks in the woods near our house. My father wasn't a scientist, he was a uniformed salesman, but he had this incredible way of thinking about things. He'd point at things and ask me questions. Not to test me, but because he was genuinely curious about how the world worked. One day I asked him, "Dad, how does time work?" And you know what he said? He said, "Richard, nobody knows what time really is. But I'll tell you what we do know." Then he pointed at a tree. See that tree growing? That's a change. See that stream flowing? That's a change. See your shadow moving across the ground? Change. And he looked at me and said, "Time is what we invented to organize all these changes. Without change, there'd be no time. Nothing would happen. It would be like a photograph, frozen." That stuck with me my whole life. Time is change. Now let me tell you about a guy named Albert Einstein. You've heard of him, right? Wild hair, genius, the whole deal. In 1905, he was just a kid really, working in a patent office in Switzerland, and he figured out something that nobody else had figured out. Something so strange that even today, over 100 years later, most people don't really believe it in their gut. He figured out that time is not the same for everyone. Now, when I say this, you're probably thinking, yeah, I've heard that before. Time flies when you're having fun, drags when you're bored. No, not that. I'm not talking about psychology. I'm talking about actual physical, measurable time running at different speeds for different people. Let me give you an example. Imagine you have a twin brother, and he's an astronaut. Lucky guy. So he goes up in a rocket ship, flies around really fast, close to the speed of light, and comes back. When he lands, you go to greet him at the landing pad. And you know what? He's younger than you now. Actually, physically younger. His clock ran slower while he was moving fast. Less time passed for him than for you. This is not science fiction. This is real. We've measured it. We've put atomic clocks on airplanes and flown them around, and when they land, they're behind the clocks that stayed on the ground. By tiny amounts, nanoseconds, but measurably behind. Wait, that doesn't make sense. How can time run at different speeds? Time is just time. I know, that's what everyone thought. But let me tell you how Einstein figured it out, because the story is beautiful. Einstein started with one simple fact. The speed of light is always the same. No matter how fast you're going, no matter which direction you're moving, you always measure light traveling at the same speed. About 186,000 miles per second. Now this is weird. Let me show you why. Imagine I'm standing on the side of a road, and a car drives by me at 60 miles per hour. Then another car drives by, also at 60 miles per hour. Now imagine you're in that first car going 60. What speed do you see the second car going? 0, because you're going the same speed. Exactly. You're both going 60 relative to me on the side of the road, but relative to each other, you're not moving at all. This is common sense. Speeds add and subtract depending on how you're moving. But light doesn't work this way. If I'm standing here and I shine a flashlight, the light goes at 186,000 miles per second, right? Now imagine I'm on a rocket ship going 100,000 miles per second, and I shine the flashlight forward. You'd think the light would now be going 186,000 plus 100,000 miles per second, right? That's what common sense says. But nature says no. You measure it, and the light is still going 186,000 miles per second. Not 286,000, just 186,000. The same speed as always. That's impossible. That's what everyone thought. But it's true. We've measured it 1,000,000 times. Light always goes the same speed. So Einstein asked himself, how can this be? How can light always have the same speed no matter how fast I'm moving? And after thinking about it really hard, he realized the only way this can work is if time itself is flexible. Time has to run at different speeds for different people to make the speed of light come out the same for everyone. Let me give you Einstein's famous thought experiment. It's genius. Imagine there's a train station. You're standing on the platform. The train goes by really fast, close to the speed of light. Right as the train passes you, 2 lightning bolts strike. One at the front of the train, one at the back, and they strike at exactly the same moment. You see the 2 flashes at the same time, so you say, yep, those lightning bolts struck simultaneously. But there's a guy on the train sitting right in the middle, and because he's moving forward toward the front of the train, He sees the flash from the front lightning bolt before he sees the flash from the back lightning bolt. Now here's the question. Did the lightning bolt strike at the same time or not? You say yes. The guy on the train says no. The one in front happened first. Who's right? You're both right. That's the point. There's no absolute time. Simultaneous. The idea that two things happen at the same moment depends on how you're moving. In your frame of reference, standing on the platform, the bolts struck at the same time. In his frame of reference on the train, they didn't. And there's no way to say who's really right. You're both right in your own reference frames. This means there's no universal now. There's no cosmic clock in the sky that tells you what time it is everywhere in the universe. Time is local, personal, relative. What this really means now, I want you to really think about what this means. You know how you imagine the universe? There's you here, your friend in China, someone on Mars, stars billions of miles away, all existing right now at the same moment in time. That picture is wrong. There is no right now everywhere. Now for you is different from now for someone moving past you at high speed. You can't even agree on what's happening at the same time in distant places. It gets weirder. You know how you think of time as flowing? Past, present, future, one after another like beads on a string? Einstein's theory says that's also wrong. Past, present, and future all exist. They're all equally real. They're all out there in something we call space-time. You're not moving through time like a train moving through space. You're a four-dimensional object stretched out in time from your birth to your death. You at age 5 and you right now and you at age 90 are all part of the same thing. The same four-dimensional object, like different slices of a loaf of bread. Wait, so the future already exists? In the equations? Yes. In space-time, past, present, and future are all there. Your entire life, already laid out. But then, do I have free will? If the future already exists, isn't everything determined? Aha! Now you're asking the good questions, and I'm going to give you an annoying answer. I don't know. Nobody knows. Maybe free will is compatible with the future existing. Maybe you freely choose things that are nevertheless laid out in space-time. Or maybe free will is an illusion. Or maybe there's something about consciousness and quantum mechanics that changes the picture. I don't know. But see, this is what's so exciting. We've learned something profound about the structure of reality. That time is relative, that space-time exists, but there's still deep mysteries. Now let me tell you how we know all this is true, because I don't want you just believing me. You should never just believe somebody. You should ask, what's the evidence? First, there's what we call time dilation with moving clocks. Put a clock on a fast airplane, fly it around, bring it back, it's behind. We've done this. It works exactly as Einstein predicted. Second, there's GPS satellites. You know those things that tell your phone where you are? They only work because we account for relativity. The satellites are moving fast and they're farther from Earth's gravity, so time runs faster for them than for us on the ground. If we didn't correct for this, GPS would be off by miles within a day. Third, and this is my favorite, there are particles called muons that are created in the upper atmosphere when cosmic rays hit. These muons travel toward the ground at close to the speed of light. Now muons decay, they fall apart after about 2 microseconds on average. Here's the problem. Even traveling at the speed of light, a muon should only make it about 600 meters before it decays. But the upper atmosphere is about 10,000 meters up. The muons should never reach the ground. But they do reach the ground. We detect them all the time. Why? Because from our perspective, the muon's clock is running slow. It's moving so fast that time dilates. That 2 microseconds for the muon is more like 20 microseconds for us, giving it time to reach the ground. And here's what's really cool. From the muon's perspective, it's not that its clock is slow, it's that the atmosphere is squished. The distance from the upper atmosphere to the ground is contracted to only 600 meters. So it does decay in 2 microseconds, but that's enough time to cross the contracted distance. Both perspectives are valid. That's what relativity means. Okay, now I want to tell you about black holes, because this is where things get really wild. Gravity slows down time. The stronger the gravity, the slower time runs. On top of a mountain, time runs faster than at sea level, by a tiny amount, nanoseconds over a lifetime, but measurably faster. That's why atomic clocks at different elevations tick at slightly different rates. Now imagine something with really strong gravity, like a black hole. Near a black hole, gravity is so strong that time slows down dramatically. If you could hover just outside a black hole and watch someone far away, you'd see them moving super fast, like a movie on fast forward. Meanwhile, they'd see you moving in slow motion. And if you fell into a black hole, from your perspective, it would take a finite amount of time. You'd cross the event horizon, point of no return, and keep falling toward the center. But from the perspective of someone watching from far away, they'd never see you cross the event horizon. They'd see you get slower and slower and slower as you approached it, like you're frozen in time, taking forever to fall in. Both perspectives are correct. You do fall in, and you your own time. But in the time of the outside universe, you never quite make it. There was a movie a few years back, Interstellar, and they got this right. The guy goes down to a planet near a black hole, and every hour he spends there, 7 years pass back on Earth. That's real physics. That's what would actually happen. Let me tell you my favorite story about time. It's about my wife, Arlene. When I was working on the atomic bomb at Los Alamos during World War II, Arlene was sick. She had tuberculosis and was in a hospital in Albuquerque, about 100 miles away. I'd visit her on weekends. One day, the hospital called me to tell me she had passed away. I looked at my watch and noted the time. Then I drove down to see her. When I got there and saw the clock on the wall, I noticed something strange. The clock had stopped at the exact time I'd looked at my watch when they called, the exact minute. For a moment, I thought, is this meaningful? Is this some kind of sign? Some connection between us transcending space? Then I thought about it more carefully. The nurse had recorded the time of death by looking at that clock, and she'd come to the phone to call me. That took a few minutes. So I'd received the call a few minutes after Arlene died, and naturally I'd looked at my watch then. The clock in her room had simply stopped working, as clocks sometimes do. And because it was stopped, the nurse had used it to record the time, not realizing it was broken. No mystery, no cosmic connection. Just a stopped clock and the human tendency to see patterns and meaning in coincidences. I tell you this story because it taught me something important about time and about how our brains work. We want time to be magical. We want there to be meaning in these coincidences. We want to believe that somehow we can transcend time, that consciousness or love or something can reach across space-time in mysterious ways. And maybe that's true. I don't know. But I do know that before we jump to magical explanations, we should look for ordinary ones. Usually, the ordinary explanation is the right one. Okay, now everyone wants to know about time travel. Can you do it? Well, you're doing it right now. You're traveling through time at a rate of 1 second per second. What you mean, can you go faster? Can you jump ahead? The answer is yes. That's what time dilation is. If you get on a spaceship and fly around really fast and come back, you've jumped into the future. Less time has passed for you than for everyone else. You've time traveled forward. But can you go backward? Can you visit the past? This is where things get weird. Einstein's equations allow for closed time-like curves. These are paths through space-time that loop back on themselves. In principle, you could travel along one of these curves and end up in your own past. But there are problems. Huge problems. First, to create these closed time-like curves, you'd need exotic forms of matter and energy that we've never seen and probably don't exist. You'd need negative energy, stuff that falls up instead of down. Good luck with that. Second, there are paradoxes. What if you went back in time and killed your grandfather before he met your grandmother? Then you'd never be born. But if you're never born, you can't go back in time to kill him. So he lives, so you are born, so you do go back and kill him? It's a logical contradiction. Some physicists say the universe would prevent this somehow. Maybe every time you try to kill your grandfather, you slip on a banana peel or your gun jams. Maybe free will is an illusion, and you simply can't make choices that would create paradoxes. Other physicists say you'd create a parallel universe. You'd go back and kill your grandfather in a different timeline, and your timeline would continue to exist separately. But honestly, I think the simplest answer is that backward time travel just isn't possible. The universe doesn't allow it. The equations might permit it mathematically, but nature has ways of preventing things that lead to contradictions. Forward time travel, though, here's something that really bakes your noodle. Some physicists think that time doesn't really exist at all, that it's an illusion. Wait, what? How can time be an illusion? Things change. Stuff happens. Okay, let me explain what they mean. In the fundamental equations of physics, time is just another dimension, like space. The equations work just as well going forward in time as backward. There's no arrow of time at the fundamental level. So why do we experience time as flowing in one direction? Why do we remember the past but not the future? Why do eggs scramble but never unscramble? This has to do with something called entropy. Entropy is a measure of disorder. And there's a law, the second law of thermodynamics, that says entropy always increases. If you drop a glass and it shatters, the pieces don't spontaneously reassemble themselves. Why not? The laws of physics at the microscopic level would allow it. Every molecule in the glass pieces could in principle move in just the right way to put the glass back together. But it never happens because there are so many more ways for the glass to be broken than to be intact. The increase in entropy defines the direction of time for us. So in a sense, time's arrow, the flow of time from past to future, is a statistical thing. At the atomic level, it emerges from the behavior of huge numbers of particles. At the fundamental level, at the level of individual particles, there's no arrow of time. Some physicists take this further and say that time itself is emergent, that at the deepest level of reality, there is no time. It's just a bunch of quantum stuff in different configurations, and time is something that emerges when you have lots of particles interacting in complex ways. Is this true? I don't know. It's one of the big mysteries in physics right now. How do you reconcile the time of Einstein, where past, present, and future all exist in space-time, with the quantum mechanics picture, where things are fundamentally uncertain until they're measured? How do you reconcile the reversible equations of fundamental physics with the irreversible flow of time we experience? These are hard questions, really hard. And I love that, because it means there's still so much to figure out. You know what I tell my students? I tell them that understanding time is like peeling an onion. You peel back one layer and think you understand, and then there's another layer underneath that's even weirder. First you think, time is just time. It flows. It's the same for everyone. Simple. Then you learn about relativity, and you realize, oh, time is relative. It runs at different speeds for different observers. Mind blown. Then you think about the implications, and you realize, wait, if time is relative, then the whole structure of reality is different than I thought. Past, present, and future all exist. Mind blown again. Then you learn about quantum mechanics and you find out that time might be emergent, might not be fundamental at all, and you realize there's another whole layer to peel back. And the beautiful thing is, we're not done. There are more layers. We don't understand how time works at the quantum level. We don't understand how to reconcile quantum mechanics with general relativity. We don't understand the beginning of time at the Big Bang. We don't understand if time had a beginning at all, or if it extends infinitely into the past. These mysteries, these are what make physics exciting. If we knew everything, if we understood everything, that would be boring. The fact that nature keeps surprising us, that every answer leads to new questions, that's what makes it worth doing. So let me tell you what I think about time, as best as I understand it. Time is part of the structure of the universe. It's one of the dimensions that make up space-time. It's not separate from space, it's woven together with it. Time is relative. It runs at different speeds depending on how you're moving and how strong gravity is where you are. There's no universal time, no cosmic clock. Time has a direction. Entropy increases, eggs scramble, people age. This gives us the arrow of time, the feeling that time flows from past to future. But at the deepest level, we don't really understand what time is. We don't know if it's fundamental or emergent. We don't know how to fit it into a theory of quantum gravity. We don't know if the flow of time is real or an illusion created by our brains. And you know what? That's okay. That's exciting. Because it means we have more to learn. The universe is stranger and more wonderful than we ever imagined. Time, this thing that seems so familiar, so obvious, turns out to be one of the deepest mysteries we face. Every time I think about time, I'm amazed all over again. Not because I'm smart, but because reality is so much richer and weirder than common sense would suggest. That's the joy of physics. That's the joy of science. You start with simple questions. What is time? What is space? What is matter? And you end up discovering that the universe is far more beautiful and strange than you ever dreamed. And we're not done. We'll never be done. There will always be more to discover, more layers to peel back, more mysteries to solve. Isn't that wonderful? Isn't that exciting? That's why I became a physicist. And if you're curious about the world, if you want to know how things really work, then maybe you should become one too, because the universe is waiting to be understood. And time, well, time is just one of the puzzles we get to work on. Now, who's got questions?